You also have to figure out a copy.
Now we know I'm telling you what
My second draft literally did change.
That's it.
All right. So today we'll talk about scalar line integrals. Next Tuesday we'll talk about vector line integrals. But I want to recap our major new ideas. So vector field. A vector field, we assign a vector to each point in space. And the way we usually represent vector fields is F equals M I hat plus N J hat plus P K hat, where M, N, and P are functions of X, Y, and Z. So for every point in space, we get a vector. We said that F is conservative. If and only if F is equal to the gradient of some scalar function. And F is the scalar potential function. And we define an operation, the curl of F equals del cross F. And this gave us a test for conservative fields. F is conservative. If and only if del cross F equals 0. In the plane, our test was the partial of M with respect to Y equals a partial of N with respect to X. And this essentially is the portions of the curl in the plane. If we define the curl in the plane, if we said our Z hat component was 0. And then we also talked about the divergence of F equals del dot F. And the curl tells us something about the tendency of our field to cause a rotation, our vector field to cause a rotation, and the divergence tells us something about the tendency of the field to flow outward. And we'll have to wait a little bit before we give a more technical definition of that. And I just realized it's Thursday. So before the end of class, we'll have to check off homework. Nobody had to remind me. All right, so let's talk about line integrals. So the terminology line integral is a little bit unfortunate because really what we're talking about is a curve integral or a path integral. So for line integrals, scalar line integrals, we want to find the sum of some function f of xy over a path or a curve and we'll call the path or the curve C. So an example could be we have a wire in the shape of some curve. And f of xy tells us the density of that wire at a particular point. And we want to find the mass of the wire. Or we have some distribution of charges on a curve, and f of xy tells us the charge at a particular point. And we want the total charge along that curve. We could also think of f of xy as a function that's a surface that's above the curve in the plane, and we want to find the area below that curve along that path. So we have kind of a curvy fence. So that's a couple of ideas of how we can interpret a scalar line integral. And any interpretation depends on how we define our curve and our function. So scalar line integrals don't tell us about one particular thing. They can be interpreted in different ways. All right, so what we're going to do is parameterize C, and in the plane we'd say x equals x of t and y equals y of t. So we come up with some parameterization for a less than or equal to t less than or equal to b. And we assume that C is smooth. That means that that our derivatives, dx dt and dy dt, are continuous and not simultaneously zero. Whoops, smooth. That's a smooth with an accent. Smooth. All right. So let me draw a picture of how we're going to go about this. So we have this curve in the plane. There's our curve C. And I'm going to say that we're going from P0 to some, we're going to subdivide this into little pieces. So we'll say P0, P1, so these are for points P2. And then here on this little interval, we're going to call this length in between these 2 points delta S sub I, where S is the arc length. And the point here in that interval is x sub I, y sub I. So we divide the curve into small arcs, and we multiply f of xy times that little arc length. So we're going to form the sum. And this should be a familiar argument by now. Form the sum I equals 1 to n for however many intervals, how many little pieces of arc we divide that curve into. F of x sub I, y sub I times delta S sub I. So if this is our density of our wire, this is the density at that particular point, times that small little piece of length. So that would be the mass of that little length of the wire, if we're talking about we're interpreting f of x sub I, y sub I as a density. If we think of f of xy as a surface up here, that would be the area bounded by the surface along that little curve. All right, so this sum, we're going to use this as our definition of a line integral. So the sum is going to define our scalar line integral, similar to how we defined a double integral and a triple integral before. So I'm going to write that definition on the next page. All right, so we're good with the argument. Conceptually not a difficult argument. All right, so we're going to say the line integral, the scalar line integral. And apparently the students from last year's class, the line integrals were the bane of their existence. I don't understand why. The line integral, the scalar line integral of f along C is, and our symbol for a line integral, we do a single integral over our curve C. F of xy ds. And that's going to equal the limit as delta s sub I approaches 0. The sum I equals 1 to n of f of x sub I, y sub I, delta s sub I. So we take the limit as the little pieces of arc length get smaller and smaller and smaller. And then our sum corresponds to an integral. And C is a smooth curve. We're at a place where we were when we talked about multiple integration, how to evaluate. This is a nice definition. We prefer not to work with a sum. We don't have to, but we need to know how to interpret this. All right, so we're going to recall that ds is, what we saw it on our integral of the day, is the magnitude of r prime dt, where r is our parameterization of C. So we can, and this ds, the way we calculate that, another way that we way that we notated it was dx dt squared plus dy dt squared. Same thing as magnitude of r prime, just a different notation. dt. So we can say, I'm going to say we can show that the integral or path integral of f of xy ds equals the integral from a to b of f of x of t, y of t. We represent our function in terms of our parameterization times the magnitude of r prime dt. And again, r is the parameterization of C, and A is less than or equal to T, less than or equal to B. guess I should, this could be R of t. So that's how we're going to evaluate these scalar line integrals. Parameterize our curve, represent f in terms of our parameterization, substitute for x and substitute for y, and ds is going to be the magnitude of r prime dt. All right, so scalar line integrals, they're pretty nice. Pretty nice. So a couple of important notes before we start talking about parameterizations and before we start evaluating these things. So any questions on our method of evaluation?
So the magnitude of R prime is similar in idea to the Jacobian, like a transforming property to allow us to use a different system. Like you just put that as not part of the function. It's like an associated part that goes more with the dt than with the.
Well, so we said when we parameterized a curve in terms of arc length, I could go back here one step, that ds dt is the speed.
Yeah.
So it's not really a transformation. That's I guess it's similar to transformation into changing from parameterization in terms of t to parameterization in terms of arc
And then
length.
the magnitude of R prime is more like, but it doesn't. The magnitude of R prime is not necessarily associated with the f of x part.
No,
it's more associated with the,
associated with the ds,
yeah.
the ds
Okay.
portion.
Excellent.
All right, so some notes. A parameterization. Introduces an orientation. To the curve. So the way we parameterize it tells us which direction we're moving along the curve. So you have to be careful if you need to move a specific direction, you need to be careful with how you parameterize. So depending on how you parameterize, you move different directions along the curve. Essentially, you're saying, with this parameterization, this direction along the curve is positive. So there's one important note. The second one, if f of xy equals 1, the integral along C of f of xy ds. Well, if f of xy is 1, the integral of along our curve of ds is what? Arc length. So scalar line integrals are related to arc length integrals.
Arc length is just a special case.
Arc length is a special case of a scalar line integral, where f of xy is just 1. If f of xy is positive, I'm going to say greater than or equal to 0 along C, we can think of the scalar line integral as an area. So let me draw a picture. So if we have our three-dimensional coordinate system, and we have a curve in the plane. So here's C. And we have some function, z equals f of xy, up here above this curve. There's our surface. Well, if we project this up, we get a projection of this curve up on the surface. We can think of the scalar line integral as the area of this lateral surface along here. So we have a fence that's in the shape of this curve. The height of the fence is defined by z equals f of xy. The line integral represents the area along that fence. What's that, Sam? So this is just, I'm projecting these down, the points that correspond on the surface to the point on the curve.
Why?
These are the fence posts. They go from the ground up to the surface. And this is a portion with a really bad paint job along the fence.
So that would allow you, so if you were buying your material to make your fence in big, long sheets, it would
Right,
tell you
right,
how
the
many-
area,
how much you need to buy.
right.
Wow, how useful.
And we can make similar arguments for f of x, y, z. So we can have f of x, y, z ds, make a similar argument about how we evaluate that. We'd have to interpret that a little differently. And the last note is if C is piecewise smooth. We make a union of smooth curves. So for example, if we had our curve in the plane was like this. Look like that, and then it looked like this, and then it looked like this, and then it looks like this, and that's our curve, that's C. And we're traveling along the curve like so. What we would do is divide this into, call this C1, call this curve C2, C3, C4, and we parameterize each one separately and evaluate the line integral along each curve and along each boundary that we get with our parameterization. And again, any physical interpretation of the line integral depends on our interpretation of f of our function and what the curve represents. Now what we're going to do with vector line integrals is we want to sum a component of a vector only in the direction of the curve. So if we're traveling along some arbitrary curve in space and we have, say, a force, we want to find the work done traveling along this curvy path. So that's what we're going to do with scalar line integrals. Or sorry, vector line integrals. All right, questions so far? Let's talk about finding parameterizations, because when we do line integrals, we have to parameterize our curves. Your curves are not always going to be parameterized for you. We're big Calc 3 students now. No, you can definitely drop.
Sorry, what is that word?
That, but your the code on your form will say WF.
What a failure.
And it means withdraw fail.
But the thing is, we're in this class, we've obviously had enough math credits to graduate. Think about it.
Think about it.
But if we fail our math the senior year, do you really think our college?
Yeah, we'll probably go.
You gotta get the thing with
I mean, it's always a gamble. You know?
Without risk.
As a wise man once said, college is a scam.
Who said that?
You better go boots.
Hey. I tried holding it, it doesn't work.
What are these words?
So we want to find a piecewise smooth parameterization of C. And here is our curve. And we're going around this direction.
Is that a circle or an oval?
This is C. And this is x squared over 16 plus y squared over 9 equals 1. That's our curve. And we're traveling around it counterclockwise. So we've talked about this before. We talked about this in chapter we did parameterizations in chapter 12.
Sure.
So it's kind of circular. We have this x squared something, y squared something equals 1. What should that make us think of? What's that? Sines and cosines.
Right.
Because we have our Pythagorean identity, right? So we let x equal 4 cosine t, y equals 3 sine t, for 0 less than or equal to t, less than or equal to 2 pi. And that way, x over 4 is cosine t, y over 3 is sine t, x over 4 squared plus y over 3 squared equals 1. And this way we also travel in the right direction, because when t is 0, x is 4. And when t is pi over 2, x is 0. So we're traveling in the right direction.
So if it was clockwise, then we'd switch the sign.
Switch to sine and cosine, yes. So we would say r of t is 4 cosine t I hat plus 3 sine t j hat. And that would be our smooth parameterization, piecewise smooth parameterization of that curve. That's a nice, this one would not be too bad to work with. Magnitude of r prime, not too bad. How about this one? All right, this is supposed to be, let me undo that. That's supposed to be horizontal. I just make it a little more horizontal. There we go. And we're going along here, and along here. And this is my curve C. And this portion is y equals x squared. This point is 2, 4. And this point is y equals 4. So there's our curve. We want a piecewise smooth parameterization. So this one we do need to make a piecewise parameterization. I'm going to call this one C1, this one C2, and this one C3. We've done problems like this in the past, but in the past we were just parameterizing the curve. Now we're going to parameterize them to do something with them. All right, for C1, how do we want to parameterize that? x equals t, y equals t squared, and we're going to let 0 less than or equal to t less than or equal to 2. And we could turn this into a vector valued function. How about for C2? Well, y has to equal 4. Let x equal t. And what are going to be our limits for t? 2 to 0, right? X is going to go to 2, from 2 to 0. So we're going to say 2 greater than or equal to t greater than or equal to 0. So we're going to go from 2 to 0 to go the direction that we want. To make sure we go the right direction. And how about C3? X equals 0. That one's nice. Y equals t.
4 to t to 0. Wow.
4 greater than or equal to t greater than or equal to 0. So we're going to go from 4 to 0.
Would you get negative values?
Possibly. Possibly.
Would you subdivide the area above that curve?
So for the area above the curve, you should be okay.
Right, because if you have a negative value, you just take the absolute.
Right, right.
That does one in this direction matter.
No.
Oh, if you're going 2 to 0, you call that your dx is negative. That's
Right.
You're going backwards to bounds.
What is another way we could do either this parameterization or that parameterization and go from 0 to 2 or 0 to 4? Negative t?
That's not going to work.
No?
4 minus.
4 minus t or 2 minus t and go from 0 to 2 or 0 to 4. So you could-
Work on closed figures,
no,
so it doesn't have to be a bounded shape. It can
no,
just be a-
it can just be some path. You just have to make sure you end up at the point where you want to end up. Where you want to end up.
And then what happens, so we're actually, by doing this, we're generating a lot of duplicate values by having it go from 0 to 2, and then having it go from
Oh,
0.
yeah.
What's
So
happening at point 2?
we probably should do this, and then maybe do this. Yeah.
So then how do we decide which value we want? Just make sure we're not generating.
If you're just going to evaluate this integral from 0 to 2, this integral from 2 to 0,
Okay.
this integral from 4 to
So it
0.
doesn't matter. They
Doesn't
should all
matter.
line up.
Right.
Since it's a nice function above,
Right,
it should
right.
all just line up and be okay.
All right. Other questions? All right. Let's evaluate a couple of these things.
Oh, yeah. Let's evaluate.
This gives us a whole new realm of possibilities for integrals of the day.
Oh, God.
So our path C, our curve is given by this one. It is parameterized already. Ti hat plus 2 minus t j hat. 0 less than or equal to t less than or equal to 2. Well, this one's nice. We need the magnitude of r prime. Well, r prime is I hat minus j hat. So the magnitude of r prime that we're going to put into our integral is just square root of 2. So this is very similar to our integral of the day. But now we have this function in here. So we get the integral along our curve of 4xy ds is going to be the integral from 0 to 2. Well, x is t, so we get 4t. Y is 2 minus t. So we have to substitute for our parameterization. And then we get the magnitude of r prime dt. Nice easy integral to evaluate. This one turns out to be 16 square root of 2 over 3. So if this were the density of this wire in the shape of that path, that would be the mass of the wire between 0 and 2. You could. We won't. We don't. Really, what we do with scalar line integrals is learn about scalar line integrals to develop the idea of vector line integral. The vector line integral is what's going to be more important for us. All right, let's look at another one. We want to evaluate the integral along C of x squared plus y squared ds along this path, which is counterclockwise around x squared plus y squared equals 4 from 2, 0 to 0, 2. Well, what is this? Let's draw a little picture. What is that thing? That's a circle. Nice circle. And this, we're going from 2, 0 to 0, 2. So we're going along here. And so that's our that little purple thing is our curve. Well, we need to parameterize this curve. Isn't parameterize a nice word?
Yeah. Very long.
It's, parameterization is even nicer. Let's find a parameterization for this curve. All right. Yeah, an orthogonal parameterization.
You just sound like you know what you're doing.
All right, how are we going to parameterize this? X equals 2 cosine t, so we go the right direction, and y equals 2 sine t. So we'd say our parameterization, r of t is the vector valued function, 2 cosine t, 2 sine t. Standard parameterization of a circle centered at the origin with radius 4. Magnitude of r prime? 2. Is just going to be, we'd get 4 cosine squared t plus 4 sine squared t, square root of that. So we just get 2. Nice. That's nice. And so our line integral, the integral along C of x squared plus y squared, well, this is really nice, ds equals the integral from 0 to pi over 2, x squared plus y squared along the curve equals 4. And then our times 2 times dt. So I just get 8 times pi over 2, 4 pi.
Wow. Very
I could have just told you that.
Wow.
Yeah.
And why couldn't we have just used the arc line?
Because we have this function.
Oh.
So we have this additional, that would give us, this gives us that a factor of 4.
Yeah, it's pi t.
Oh wait, hold up.
Do you know how this can be an area?
Can it?
Is this the area? Is this the fence technique?
Yeah.
This, we could think of this, so if x squared plus y squared is the z equals x squared plus y squared up above here, that would be the area of the fence below that surface along that little quarter circle.
So this is the fence.
So, yeah. All right, questions there? Okay, last one.
What's new, Dylan? Hey, Sean, when I checked for my Essex for the third time.
And our path is going to be the line from 0, 0 to 3, 9. So this one is literally a line integral.
Guess what? X equals root y.
Is that function the inner x? Because it's on the line.
All right. Well, there is our curve, and we're going along the curve that direction. How are we going to parameterize that?
X is equal to t. Y is equal to 13.
Y is equal to 1/3 t. What's the equation of this line? Y equals 3x. There we go. So we're going to say x equals t, ti hat, plus 3t j hat. And we're going to go from 0 less than or equal to t less than or equal to 3. Magnitude of r prime. I like that one, Sean.
Did you get on the last test, John? Pull out big guns.
Magnitude of r prime. What does magnitude of r prime come out to be? Square root of 10. So our integral, x 4 plus 4 square root of y. ds is going to equal the integral from 0 to 3 of t plus 4 square root of 3t times 10 square root of 10, something with a 10 in it. Easy integral to evaluate. This comes out to be 57 square root of 10 over 2. All right, questions? Okay.
I'm assuming it's going to be the same problem as last unit, where it's just algebra.
Evaluating, yeah, sometimes evaluating the integrals is not as nice. And parameterizing the curves, that tends to be a, students forget how to do that.
I will be super high on that.
I am certainly going to forget how to parameterize curves. That seems like a very empirical type situation.
All right, there's that. We have our